Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I am your guide, Dr. David Irvin. Today we'll be discussing Chapter 1, Part 2, Covalent Bonding and Shapes of the Molecules here. So the next part of this, now that we know that we have electrons and different energy levels, now we're going to start talking about the Lewis structures and Lewis bonding of how we look at organic chemistry. Okay, so the most important thing about this is that we're going to play with the valence electrons. So in carbon and a lot of the molecules, a lot of the atoms that bond to carbon, we're dealing with that number 2 energy level, that 2s and those 2p orbitals. Okay, the valence shell is the outermost electron shells. If there are any electrons covering an inner shell, those inner electrons do not bond, they just stabilize the atom. The outer electrons are the ones that bond. Okay, so the valence shell is the outermost shell, and the valence electrons are the electrons that are in those orbitals that we can deal with to make it our chemical bonds. Okay, so what this did for us in helping describe the atom is the Lewis structure of the atom gives us a way of looking at what the atom will have. And so usually we do it by the symbol from the periodic table. So for example, carbon would be a C, and then we add dots to represent the valence electrons that are the ones on the outside shell that we're going to deal with when we start making bonds to carbon. Okay, so like I said before, we can look at the different electrons that are on those valence shells. Again, it's only the outside one. So if we looked at this table here and we went and said, okay, hydrogen as a neutral hydrogen only has a one electron in an s orbital, and that's the only electron it has. Therefore, that's its valence electron. Okay. If we look at lithium here, it has 2 electrons on its inner shell, but those are its inner shell. We now have its outer shell, so we have 1 electron on that outer shell. And if we look at sodium down here, again, it has a 3rd energy level. We're looking at that 3 energy level, but we only have 1 electron on that outer shell, so that's our valence electron, the 1 electron that's on the outer shell. If we look at the other elements here, for example, boron has 3 electrons on its outer shell. Carbon has 4 electrons on its outer shell. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And the noble gases all have 8 on their outer shell, which makes them less likely to react. Okay, so do we have to memorize this chart? No, we don't, because remember, we can use the periodic table of elements to tell us how many electrons are in that outer shell that we're going to play with. Okay, so when we look at the periodic table, if we look at these A numbers in our columns, like A1, A2, and these 3A, 4A, 5A, 6A, 7A, that tells us how many electrons are in our valence shell. And so we can quickly assign the fact that nitrogen being in a 5A group means it has 5 electrons in its outer shell. So we have to account for 5 electrons when we're bonding. Fluorine right here is in the 7A, which means it has 7 electrons that we have to deal with when we're looking at the valence electrons. Okay, so you don't need to memorize anything, you just have access to a periodic table of elements. Okay, so in the Lewis model of bonding is that atoms are bonded together in such a way that they want to have the electronic configuration that has the filled outer shell. Okay, there's a couple different ways it can have that filled outer shell, that be like a noble gas and have those 8 electrons in that p orbital, in that s and p energy level. Okay, one way to do that is that it can lose an electron or gain an electron. For example, when lithium only has that 1 electron at the end, it's easier for it to lose that electron and become a positive charge. So if we lose an electron, we no longer balance the number of protons inside. We come up with a cation or a positively charged ion. If it was something like fluorine, which only needed 1 electron to fill that shell, it'd be much easier for it to accept an electron and become an anion or have a negative charge on it. Okay, so we can do a thing where we transfer those electrons. And when we do that transfer of electrons from one to the other so that they become ions, we now have an ionic bond, okay? Now, there's a lot of different materials that make ionic bonds. For example, metals and nonmetals tend to make very strong ionic bonds, like sodium chloride or lithium fluoride. Those are very common. However, as we get to the elements closest to carbon, we're more likely to form what we call a covalent bond. And in a covalent bond, we're not going to give away those electrons. We're just going to share the electrons we have with the molecule or the atom next to it. And when we share those electrons, that means that I can have them part of the time, you can have them part of the time, and we can have the full number of electrons we want to have. So in organic chemistry, we want to classify all of our chemical bonds as either ionic, where they've given up electrons and have charge. A polar covalent, meaning that we're sharing electrons but not equally. And then we have non-polar covalent, which is where we're sharing electrons equally among two atoms. And the way we can tell the difference from this is looking at the difference in the electronegativity between the atoms that are bonded. Okay, so ionic bonds, covalent bonds, and polar covalent bonds are all having to do with the electronegativity of the atoms adjacent to it. Okay, so let's talk about electronegativity. Electronegativity is just the measure of the force of an atom's attraction to electrons it shares in a chemical bond with another atom, okay? Which really means that how much do you really want that electron, okay? So when we look at electronegativity, electronegativity increases as we go across the table and as we go up the table. Okay, which means fluorine is our most electronegative atom. It is the most likely to want to take away electrons from somebody else. Okay, so then that means as we go the other way and go down, that becomes less and less likely to try to steal an electron and more likely to give away an electron. So if you look at the stuff on the left side of the periodic table, those are more likely to be positively charged ions. And those nonmetals closest to the noble gases are more likely to be negatively charged ions. However, the different types of bonding is also described by the difference in that electronegativity. Okay. So now that we know that electronegativity increases as we move up and it decreases as we move over, and that fluorine is our most electronegative atom, let's talk about the relative spacing of what we can have happen in this region where we have carbon, okay? So if we look at the absolute values or the values for these atoms, we'll see that there's a trend here. So we have fluorine being our highest at a 4, and way down here, we have some of our lowest one is this 0.7, okay? So what that means is if we had a compound with cesium and fluorine, it would definitely be an ionic compound because they are very, very different. However, the fact that oxygen has a pretty high electronegativity and fluorine has a high electronegativity, does that mean that we're going to form only one kind of bond there? Maybe, maybe not. Let's take a look at why that happened. The difference in that electronegativity is going to tell us what kind of bond it has. Okay, so if the difference in the electronegativity is less than 0.5, that means we're going to have a non-polar covalent bond. Okay, now think about it, is that, okay, they both kind of want to tug on the electron the same amount, okay? So that they're going to just kind of push and pull, okay, we're just going to share it, it's going to be fine. We're going to share it evenly between us because we have about the same desire to have this electron. Now let's say we have two different atoms. One is much more electronegative, like fluorine, but one is less electronegative, like carbon. So the difference between that is about 1.5, okay? So that means we're going to form a covalent bond because we're still going to share. I don't steal your electrons away, but we're going to share, but it's going to be pulled more toward the electronegative element. For example, fluorine, as opposed to carbon, giving us a polar bond, but it's going to be a covalent bond because we're still sharing electrons. If the difference in electronegativity gets so high, greater than 1.9, what's going to happen is the less electronegative atom is just going to give its electron to the more electronegative atom, and we'll form a negative charge on the more electronegative atom, positive charge on the less negative atom, and we're going to form an ionic compound. Okay. So the threshold here is 0.5 or less is a non-polar bond. 0.5 to 1.9 is a polar covalent bond, and greater than 1.9 is an ionic bond. So these different types of bonding classifications give us different reactivity. All right, so let's look a little deeper into that ionic bond. Why would it want to steal that electron away if it's just more electronegative? And if we look at the electronic structure here, there's only one electron in that third energy level of sodium, okay? Now, orbitals like to be empty, half full, or completely full, okay? So that s orbital is half full, so it's a pretty happy orbital, okay? In fluorine right here, we only have 5 electrons in those p orbitals. It would prefer to have 6, okay? And it's a very electronegative atom, and so it's more likely to steal the 1 electron away from sodium. Now look at the electronic configuration. Sodium now has 2 complete energy level shells. It's completely filled its 1 energy level, and it's completely filled its 2 energy level. Fluorine has completely filled its 1 energy level and completely filled its 2 energy level. They both have completely filled orbitals, which means these make very good, very stable ions. Now that we have a positive charge and a negative charge, those can be attracted together to give us that ionic bond. Okay, so how do we show this electron moving from one atom to the next? Well, what we can do is we can say, okay, there was 1 valence electron on that sodium, okay? And there were 7 valence electrons, that outer shell, on fluorine. So what we're going to do is we're going to take and draw a single-headed, 1 barb, means 1 electron. 1 barbed arrow is going to be transferred from the sodium to the fluorine to create 2 ions, a positive and a negative, and therefore it's going to form an ionic bond. Okay. Let's look at that in polar covalent compounds. Okay. In a compound like hydrogen chloride, right here, the hydrogen is less electronegative than the chlorine, okay, but it's not big enough to make it fully ionized, okay? It's just a polar bond. So that means the chlorine is going to pull some more electron density to it than the hydrogen can pull to itself. Therefore, more of the electron density is going to be on the chlorine. Now, if we completely gave that electron away, that chlorine would have a negative charge, but it's only pulled some of that electron away, which means we have a partially negative charge because it didn't take the entire electron, it only takes it most of the time. What that means is if the electron is being pulled away from the other atom, in this case hydrogen, it's going to be partially positive because while it's sharing the electron, it spends more of the time with the chlorine. Okay. Now, when we map this out to kind of help us visualize this, we typically say negative charges are represented by the red color and positive charges are by the blue color. And if you have a green, that tends to be a non-polar or non-polarized bond. Okay. And that concludes the section of Chapter 1, Part 2.